It's my pleasure to introduce Dr. Jigeni sir. Sir is currently working as assistant professor at Government Vidarbha Institute of Science and Humanities. He has completed his master's degree from Sri Shivaji University, Kolhapur, followed by SEC exam in 2011. He has completed PhD from Solapur University in 2013. As of now, he has published 21 research papers in various national and international journals. Now, I would like to call Dr. Devde Madam to felicitate Dr. Jigeni sir, chairperson for today's session by offering memento and chaplain. Now, I would like to call upon stage Dr. Bijwe sir to felicitate Dr. Digambar Natargi sir. Now I call upon stage Manjusha Pawar madam to felicitate Dr. Abhijit Yadav sir. I request Dr. A.V. Rajgure sir to felicitate Dr. A.R. Nemare sir. Now I hand over the session to Dr. Jigeni sir and request him to introduce resource person. Please sir.
Good morning. Thanks for organizer for giving me opportunity to introduce today's speaker, respected Nadari sir, who did his PhD from Shivaji University, Kolhapur. The title is on materials of aerojets under the supervision of well-known researcher Rao sir. And as far as the research experience is there, now he is a RA as a research associate in Punyashlok Ahilyabai Holkar Solapur University, and also he's worked as a Chief Technical Officer in France and postdoctoral fellow of Swiss Federal Research Laboratories for Material Science and Technology, Switzerland. And also he had SRF, JRF. And apart from this one short research experience, awards and honors are there also. Best 10 business ideas, that is EIT Raw Materials Business Idea Competition in Raw Materials, France 2016. And also he awarded as a second prize award for business ideas, EIT Raw Materials Business Idea Competition in Raw Materials, France 2016. Apart from Maharashtra government, the Young Associate in Physical Science, means in the physics, in the 2021, in the last year he got the award. And as after this awards and honors, he completed near about 6 projects he completed, and whatever the amount is there is on a euro foreign project he completed, and 2 ongoing projects are there. And these are the near about, and one is a confidential related with the research work he said, that's why he not mentioned. And in all 9 projects, see his work on that one. And publications and reviewer experience. Peer-reviewed journals is 40, H index is of 20 is there, and the citation is 2021. Book chapters 4, and served as the reviewer role for renowned science journals. And he attended the conference, especially of award conferences, poster presentation in international seminar on aerogels, Mainz, Paris, Text, PSL Research University, France, and also he attended the international seminar on aerogels in Germany, and attended a Materials Day, Department of Materials in Zurich, and he presented oral presentation on hybrid materials in France in 2011, and worked on a hydrocarbon sorption behavior in elastic superhydrophobic silica aerosols, where he presented poster presentation in the International Symposium Transport in Porous Materials and in Network Microstructures 2010 August in Belgium. This is Switzerland. This is a brief introduction of today's first guest lecturer, Mr. Dr. Digambar Nadargi. So I request him to deliver a lecture.
आपण हे लॅपटॉप इथे ठेवूया का? हा चालेल का? हा चालेल.
ट्राय करू द्या मला. ओके हो गया सर, ये झालं. तुम्ही सोडून द्या परिमल सर. ओके
स्लाइड ऑन करा.
हे क्लोज करू. कुठून आहे तू? तिथून ओपन करून द्या पहिले, मग मी ऑपरेट करतो.
ऍडव्हान्स मध्ये जाऊ.
ऍडव्हान्स मध्ये जाऊ.
कोणतं?
पॉवर पॉइंट खाली पॉवर पॉइंट होतं ना.
पहिले ते हा पीपीटी ओपन करून ठेवून द्या. आता मिनिमाइज करा ते. आता शेअर करा. शेअर झाली का पण?
काय करा आपण नेक्स्ट करायचं नेक्स्ट स्लाइडवर राहा. नेक्स्ट म्हणतो त्याला
नक्की पाठवा.
तिथनं मला बॅक जाता येणार.
बॅक तुम्हाला सांगता येते तिथे. ओके सर, आता इथे पाठवतो की हे झालं ना, तुम्ही राईट करून प्रिव्हियस नसतात तिथंच, म्हणजे तुम्हाला काही प्रॉब्लेम इथून तुम्ही लेफ्ट दाबलं हे केलं तर प्रिव्हियस येतं आणि डायरेक्ट इथून कसं आहे तुम्ही हातामध्ये वापरू शकता. काय प्रॉब्लेम? म्हणजे तुम्ही आता हा जर हाताने ठेवला म्हणजे तुम्ही हो हेच तुम्हाला लावून
नाही मग इथूनच बोलावं लागेल.
दुसरे
सेटअप केलेलं राहू दे. काही नाही.
हा तेच तर म्हणत तुम्हाला कम्फर्टेबल आहे. ओके तुम्ही हातामध्ये वापरा.
तिथे लागेल. चालेल. ओके गुड. थँक्यू. Good morning all. Am I audible? Girls, am I audible? First of all, my sincere thanks to Dr. Dijani sir for kind introduction. I am indebtedly grateful to the organizing committee of this conference, Principal Ramteki sir, the IQC Director of Amravati University, Professor Wagule sir, the convener of this conference, Professor Bijwe sir, my friend, co-convener, Dr. Ashish Rajgure sir, all entire organizing committee who are actively putting their efforts to materialize this event successful. The second international conference on recent advances in material science and nanotechnology, organized by GS Tompe Arts, Science and Commerce College, Chandur Bazar District, Amravati. It's indeed a great pleasure to share my research experience with you all, especially the young, fresh, talented students, and of course, seeking the guidance from the experts present over here. And it's a great opportunity to meet you all after a long time. And first of all, thanks for that. So after the breakfast, let's have some dessert. So we will start. Okay. ठीक है. Back लगाओ. हाँ. Okay. Sir, मी next म्हणतो तेव्हा move करा. Okay. End show. झाला top. आवाज आहे ना असा घुमतोय. हा ऑडिटोरियम मध्ये. चला, okay. Fine. So today we are going to discuss soldier derived advanced materials, aerogels, coatings and gas sensors. Next. So I'm gonna discuss with you the overview of social concepts in a brief manner. After that, we are going to focus on three of the main applications which are highly applicable to the routine life of our human civilization. What I feel is these social concepts are so vast, the applications are diverse range. So one cannot conclude in a talk how many can be possible applications we can foresee. So that's why I have selected three of them: aerosols, coatings, and gas sensors. And finally, we will wrap up the talk in the summary section. The picture shown over here, sir, जाऊ द्या एक मिनिट हा एक मिनिट ओके ठीक आहे मी ऑफ करतो. The picture shown over here, when I look at this picture, the thought came in my mind, and of course it's a fact, we all are living in this concrete jungle. 90% of our time we spent in the building blocks of this concrete and 10% in nature. And therefore, the major part of the research and development is focused on the comfortness of the human civilization. These research focal points majorly are renewable energy, windows and glazings, lighting, facades and super insulation, and safety utensils. Sol-gel derived advanced materials provides the best solution, the best alternative for fulfilling the needs of human society. The overview of admit करू का? Next line. Okay, आला. The overview of R&D in Sol-gel, especially when I am talking about aerogels, thin films, and gas sensor, we have so much research spreadsheet to do. For example, in this Sol-gel system, we can focus on fibers, polymer reinforcement, chemical functionalization, multi-component intercalated network, quantum dots, dyes, phosphors. In the thin films, you also have the diverse range like TCOs, LEDs, multi-layer architectures, low emissivity, IR reflective absorbers. Here also a chemical functionalization. In gas sensors, a big variety of metal oxides, amazines, chalcogenides, and many more. So really, we are fond of this Sol-gel chemistry or the Sol-gel methodology. When I show this graph over here, it's a viscosity over time. मी हे काढून हातातनं बोलू शकतो? खूप हे व्हायला लागलं. Thank you. आवाज येतोय मागे? Okay. So when I show this graph here, viscosity over time, as you see here, as the time passes, the viscosity gradually increases. This gradual increase of viscosity is not up to the end, because after percolation threshold, it shooted up exponentially and ended up into the gelation. So one can have the two possibilities over here, Sol and gel. When I divide this Sol-gel methodology, I end up with Sol and the gel, two systems. Sol is nothing but the suspension of colloidal particles. These colloidal particles are in the range of 2 to 20 nanometers. These colloidal particles, when I do some magic reactions, hydrolysis, condensation, something like that, and what I do is, these colloidal particles, I bring them together. So the monomer become a dimer, dimer become a trimer, trimer become a tetramer. In this fashion, the network structure evolves. So I start from the sole and end up into the gelation. When I divide this graph, this side I have a liquid chemistry and the other side I have a powders or the aerosols. So when I have the liquid chemistry, I have the possibility of forming the thin films either by deep coating, spray coating or spin coating. If I go to the other side of the graph, what I ended up is aerosols when you really think of drying the gel in a particular fashion. So supercritical drying and ambient pressure drying. And if you don't care about drying gels in a particular manner, you end up with the powders or the zero gels. As an example, I have shown over here the WO3 powder. This sol gel chemistry or the sol gel methodology is highly established. Traditionally, it has a long history. We are not talking anything new. So what this is traditional alkoxide route is, we start from the alkoxide precursors, the metal and oxyalkyl groups. And we start from that, we dissolve them in the alcoholic media, do some reactions, hydrolysis, condensation, as I said. So by particular acid or particular base, you go to the gelation part, of course, from sol to gel transition. And here also you can have the two possibilities. Cross-linking and condensation reaction, you can have a choice for liquid deposition and you can have the choice for gelation. Once you have a gelation, you can either go for aerosols or you can go for the metal oxide powder. The limitations of alkoxide chemistry is, for example, if you want to make a nanocomposite, two dissimilar metal ions, if you want to make it together, the problem with the alkoxide chemistry is the reaction rates of, let us say M1, the reaction rate is faster. M2, the reaction rate is slower. In that case, what happens? The reaction of first hydrolysis of the first metal ion is faster than the second one. So when you trigger the gelation, at that time, what happens? The first one, which is hydrolyzed completely, that undergo into the condensation, but the second one is partially hydrolyzed. So you have the inhomogeneous phase. Homogeneity will be an issue. Secondly, if you want to make a large choice of different composites, alkoxide precursors are not at all available. So these are the limitations. So Alex Gass from Liverpool University, USA, he is a pioneer working of this epoxide chemistry. He came up with this idea, eliminate the alkoxide precursors. We will start it from the common metal salts. Common metal salts means chlorides, nitrates, very cheap. You start from there. You dissolve it into the aqueous media. You dissolve it into the water. And by using the epoxide chemistry, one can go for the sol or gelation. So that's what the beauty of this modern epoxide route. So what happens over here? You see, this is the epoxide. Epoxide means propylene oxide, DMO, SO, anything you can take. I prefer propylene oxide because even though it is highly volatile, you can put it in the fridge and you can operate it. So what happens in this? You have this metal salt dissolved in the water and then propylene oxide is added. So this oxygen steals the proton from the central metal ion and is ended up into the hydroxide. Half of the work is done. We want the metal oxide with OH group. Okay. So once the OH group is formed, this ring opening reaction is irreversible. So you need more propylene oxide to go for the gelation. So in this way, you can have the condensation and cross-linking reaction, the liquid deposition choice or the gelation. It's up to you. So that's the beauty of epoxide assisted sol gel route. I would not say limitations, but more than that, what we can see is the epoxide assisted materials are extremely flexible. We have a large choice of elements. So over the periodic table, 70% of the periodic table you can use it by using this epoxide route, which is not at all possible in the alkoxide route because precursors are not at all available. Okay. Then it uses the simple metal salts, aqueous medium, room temperature synthesis. suitable for complex mixed metal oxide material because here is no any reaction rate. So simply the salts are dissolving in the water. So that's why it is suited for common complex mixed metal oxide materials, and you can have a control over micro and nanostructures. I hope with this a brief background, you are sufficient now to move to the application part. Let's go to the application part. The first one, aerogels. Aerogels are very fascinating material. You tune its synthetic parameters, the properties get changed. Properties get changed, the applications get changed. So you have diverse range of applications in the aerogels. If I ask you a question, can you hold air? Of course, the question itself sounds like a wrong. We cannot hold it. But if I condense this 90% of the air in 10% solid, of course, anyone can hold it. That's what aerogel is. Very fragile, brittle, sensitive to the moisture, and translucent. So let us have few examples of aerogels in color. The first example shown over here is the best thermal insulation property. You see the hibiscus flower on the aerogel sheet, and at the bottom you have a fire. The second example, since it is a low density material, one can use it for the space applications, cosmic dust collection. It is translucent, so one can use it for the rooftops. Of course, these are oleophilic and hydrophobic. Means if you have a mixture of oil and water, aerogel is oleophilic, so it absorbs the oil and repels the water. So accidental release or deliberate release of oil on the seashore, one can clean it with aerogel. And the last one is the flexible aerogels. These flexible aerogels, one can use it for the shock absorbing material. This photograph shows the examples of two aerogel projects, the demonstration projects in Switzerland. This one is a single family house where we have used aerogel granules as an insulation material because outside the temperature is so cold, you cannot afford all the time heater on. So aerogels as an insulation material will be used. In the same way here, in a gymnastic hall of the high school in Zurich, we have used it as a transparent roof. This example shown over here is the joint venture of EMFA and Zurich University of Arts. We built it together, this mobile living or work container, one can say. It's a self-sufficient container. Aerogels are used in the outer jacket of this container. So it can work without any electricity in the -°C. So you don't need any heaters inside it. I understand how to go from sol to gel, but when the question comes from gel to aerogel transition, here needs some skills. The practical difficulty in replacing the gel liquid by air without any shrinkage is really a challenge. So this Laplace pressure, you can see here, capillary pressure PR is equal to -2 gamma cos theta by R. The gamma is the main role playing here, surface tension. If I prepare the gel with using alcoholic media, now I want to remove gel. You can imagine आपले gel chocolates असतात. That's the gel. त्यातलं जो पाणी आहे ते मला उडवून टाकायचं, right? So this water, I want to take it out without any shrinkage in this gel body. Imagine करा, मी जर समजा ते पाणी एका टेक्निकने काढलो, जेल जसं आहे तसं ते प्रिझर्व राहणार. It means it is highly porous. Okay, how I going to do that? So the liquid which is enriched the gel, you take it its supercritical temperature and pressure. At that point, there is no any meniscus, means surface tension is automatically zero. Once gamma is zero, the capillary pressure is zero. In this case, you end up with no shrinkage. So wet gel volume is equal to aerogel volume. So whatever the gel body was there, when you dry it under supercritical conditions or ambient pressure drying conditions, you end up somewhere like very nice spongy gels. From the diverse list of applications that we have worked on, few of the examples I would like to show over here. The first example is flexible and superhydrophobic aerogel. In the beginning, I told you aerogels are very sensitive to the moisture. They deteriorate with time. So one target is to make them hydrophobic. And second, they are very brittle. So the another target is to make them more flexible. How we gonna do that? So we choiced some of the alkoxides which are alkyl attached alkoxides. So methyl triethoxysilane, like methyl trimethoxysilane. These are the alkoxide precursors where one group is already like an umbrella, hydrophobic group, and the other ones only 3 branches. You can imagine if you have 4 hands and everyone holds it, you are packed. But one arm is not attached to anyone, you are quite flexible. The same phenomena here. One arm is free. This one, you can see this one. So the attachment is in between this. So when you have the less polymerization, you ended up into the flexible structures. And when you have the extensive polymerization, rigid structures are evolved. When I say extensive polymerization, less polymerization, it means what? Simply the concentration of the precursor. If precursor I diluted more, then the polymerization is less. If concentration is too high, then it is an extensive polymerization. I confirm that by using this TEM, where you see concentration is very high, so extensive polymerization. When the concentration is too low, then the polymerization is not too rigid. We see here the maximum possible bending of this aerogel as you tune the concentration parameter. This graph is shown over here is the uniaxial compression test measurements, where the aerogel tube and on the top we have mass loading like Young's modulus, the same experiment we have done. And we have seen that when we increase the concentration, then for example here, there is no any change in the length. But as you tune the concentration at highest dilution, you have a highest compression. Nearly 50% of the aerogel tube, you can compress it. So Young's modulus, you see it here, 15, and in the other case, it is 3 into 10 raised to 4 Newton per meter square. That was the story for sophisticated applications. The common man needs something cheaper and sasta bhi ho or durable bhi ho, something like that. So inexpensive water glass fiber aerogels, the granules we have prepared. This we can use it for the insulation purpose. The main motivation to use these fibers inside, they are very fragile. I want to make them for more life. So fibers modified aerogels are used. Oh shit. The third example is the ambient dry synthesis of SiO2 aerogels. These aerogel slabs, you can see it, we have vented from prototype to pilot scale. It's an excellent thermal conductivity, rigid, less dust, and we can do the solvent recovery. Since it is an ambient pressure drying, we need a lot of solvents, hexanes, ethanols. So these solvents you cannot just throw like that. So we can use it batch-wise after cleaning them. Next example is the luminescent aerogels. You imagine that the picture where the lighting was also a research focal. So one can use it, the aerogels, for a platform technology for LED lighting. So it acts as a diffuser. So it's a very beautiful decorative purpose. So from solid to gel transition, simply you add the nanoparticle pigments, dye particles, and you end up somewhere with really nice kind of aerogels. So that's the story about the aerogels. Now let's move to the coatings part. So you see, I started at the other side of the graph, and now let us see at this side of the graph. Thin films, in the thin films and coatings, transparent conducting oxides, surface pattern metal oxides, electro or photochromic coatings, hydrophobic and hydrophilic coatings, and low K coatings. Of course, there are diverse range of applications in this as well. Let's see few of them. TCOs, transparent conducting oxides. It's not a new story. From many decades, people are working on that. What new we are doing here? You know the new route of epoxide chemistry. Let's use that. And the innovation is high throughput synthesis. So by using the robot, you tune the synthesis parameters in a one shot and you make the different types of TCOs. That's the innovation in this part. So we have tested the antimony dope tin oxide. The optical transmission is greater than 92%. The low electrical resistivity rho is 1.8 into 10 raised to minus 2 ohm centimeter for 9% of SB doping. So we have changed the different loading percentage and we have ended up somewhere at 9% of SB. We have the lowest electrical resistivity. The phase is confirmed by using XRD and cassistor phase was obtained. This work is published in ACS Applied Material Science Interfaces. The second example is the surface pattern metal oxides. I call it as a EMOR technique, epoxide assisted metal oxide replication. So you imagine, the sacrificial template. If you imagine a marbles in a plate, where these two marbles are connected each, you have this triangular empty space between the two marbles. One can pattern that by using this epoxide and Silar method if you make it connection. So these volumes, if we do it, the sacrificial template, we prepared it by polystyrene beads of 4 micron and then Langmuir Bladock technique. With that we have deposited on the glass films and we have made the shape of empty volumes. We have made it. And in that empty volumes, we have added this ZNO. ZNO simply not ZNO, so zinc nitrate and epoxide and water. By using the Silar method, we have patterned this. So you see here, this polystyrene template without any, it is coated with this ZNO. And when I diffuse it off, the sacrificial template, let us say at 200 degrees Celsius, this polystyrene beads goes off. You end up such a nice honeycomb structures. The second one we have tried for SNO2 patterning, the same PS polystyrene beads, and we try to coat or we try to make the same honeycomb structures. And we have obtained, instead of honeycomb structures, we have obtained the hollow spheres. Now the question comes in my mind that if I take the ZNO, then I end up with the honeycomb structure. But when I start with the tin oxide, then I ended up into the hollow spheres. Why? The formal oxidation state of ZNO is +2. Whatever the metal oxides, metal ions which have formal oxidation +2, they don't go into the gelation. They always go into the precipitation. Therefore, you cannot have this coverage, the polystyrene coverage. Formal oxidation state of tin oxide is +3, so you end up into the gelation. So this nano gelation gave up the nice hollow spheres. So this work is published in RSC Advances. Now the third example, I will just go briefly. The electro or photochromic smart windows, WO3 based electrochromic coatings. I hope you are aware of this smart windows, like curtains we use it. Instead of that, the smart windows, you switch on or you apply the potential, it colors changes. For example, WO3 is a best electrochromic material. When you apply the voltage with the particular electrolyte, then it goes to the dark blue. So automatically it acts like a curtains for the windows. Then TiO2 based photochromic coatings, you see the different colors of TiO2 based photochromic layers. Due to the different dye colors, you ended up with the different colors of this coating. The last, not last one, the second last, hydrophobic and hydrophilic coatings. Tomorrow, Dr. Latte sir is going to take a session on this hydrophobic and hydrophilic coatings. So you will get the better idea. Just as a glance, I would like to show over here, this silane chemistry can be used for preparing the hydrophilic to hydrophobic coatings by using the surface derivatization, TMCS, HMDZ or other alkyl alkoxysilanes. The optical transmission is very good. You can tune the water contact angle. This is for derivatized and this is for MTMS. You can see from 10 degrees Celsius you went up to highly hydrophobic 130 degrees. This work is also published. One can go through it. The last one is the low K coatings. The low K coatings are really a need of this modern digitalization. In the ICs, one can use the low coatings because this helps to stop the cross signaling and the switching behavior is faster, which is not possible in the alkoxys. For example, SiO2, it is not possible. The last one for gas sensors, the role of a gas sensors in our life. As I told you, if you remember still that a cottage and safety utensils is also one of the major topics. So gas sensor falls in that, where we need the gas sensors, chemical plants, water treatment plants, tunnels, power station, hospital, boiler rooms, and many more. The purpose is protect the human life, protect the production, the infrastructure, and also prevent or minimize the environmental pollution. This is really pity, but it's a fact. We have this air pollution, the photograph from Delhi, the water pollution, land pollution, the annual greenhouse emission by different sectors of our human society like waste and disposal, land use, domestic sources, fossil fuel burning, transportation. With all this, you have a really big amount of annual greenhouse emission like carbon dioxide, methane, nitrous oxide. So gas sensor plays a very vital role in such conditions. A plenty of metal oxides are used for developing the gas sensors. We are going to focus few of them. Let us first understand the process flow of developing the gas sensor. So I start from this Soldier reaction. I put them into the autoclave at some decent hydrothermal temperature and pressure. Then I filter it, wash it, dry it, sinter it, and I end up into the powder. For an example here, the sensing material is ZNO, white powder. Once I obtain the powder, I screen paint it, or you can make the Dr. Blade technique and go for the gas sensing studies. In the gas sensing, let us see the high performance WO3 gas sensors. The factors influencing the gas sensing properties are novel metal loading or even doping also, influence of the graphene loading and tunable morphology. I go briefly here. You can see a marigold like flowers we have obtained for novel metal dope WO3 powder. These WO3 nanopowders are made up of like a small sheets. They are such a compact, very nicely. They look like a marigold. Jhenducha flower. Its gas sensing parameters by using the ruthenium, the novel metal doping. By ruthenium, these are the results. One can see here only for 1 ppm. I'm talking 1 ppm. Parts per million. Eka million ekhada fक्त molecule. That's 1 ppm. That 1 ppm gives 80%, more than 80% of the gas sensitivity. Apart from all these ones, these all are in the range of 500 to 100 ppm. So you can imagine how good sensor it is. Tunable structures, you can tune these morphologies from marigold to different morphologies like the nano flowers, the nano sheets, the nano rods. These are like a nano plates. One can see here also for acetone we have obtained the good gas sensing behavior for 10 ppm. Of course, these all results are available. One can go in deep into that. The graphene loading, when we load the loaded the RGO, there also we have seen that a vast change in the gas sensing behavior. The green root synthesis of ZNO, that was for WO3. I would like to tell the story of ZNO. ZNO material, ZNO ला लोकांनी अक्षरशः कचरा करून टाकलेला. खूप जुन्या काळात म्हणजे पहिल्यांदा जेव्हा मेटल ऑक्साईड स्टार्ट झालं, गॅस सेन्सर जेव्हा स्टार्ट झालं, ZNO पासून सुरुवात झाली. आमच्याकडे एक प्रोजेक्ट होता CSIR चा ZNO बेस्ड गॅस सेन्सर. आता करायचं काय, ऑलरेडी ZNO चे एवढे पेपर्स आहेत, आपण नवीन काय करणार, ते डोक्यात होतं. ऑनलाईन मध्ये पतंजलीच्या स्टोअर मध्ये गेलो, बाकीच्या काही गोष्टी घेत होतो. एक थॉट आला, म्हटलं आपण जर समजा ग्रीन रूट सिंथेसिस केलं तर रॅन्डमली एक 3 चूर्ण हातात आले. ज्याचं एक जास्त ऍसिडिक होतं, एक गॅस साठी असतं ते एक, आणि अजून एक न्यूट्रल, असे पीएच आणि त्यांचा काढा तयार केला. त्या काढ्यामध्ये तुम्ही जेडेनोचं सॉल्ट जर मिक्स केला, यू एंडेड अप विथ रिअली नाईस प्रेसिपिटेशन ऑफ मेटल ऑक्साईड. आणि त्याचं गॅस सेन्सिंग स्टडी केल्यावर असं लक्षात आलं की हे खरंच वर्क होतं. 1000 ppm ला का होईना, पण 175 डिग्री सेल्सिअसला तो जेडेनो खूप छान ऍसिटोनला सेन्स करतो. आणि ते RSC ऍडव्हान्सेस मध्ये पब्लिश झालं. आम्हाला वाटलंही नव्हतं की हे इंटरनॅशनल जर्नलला जाईल, कुठेतरी कॉन्फरन्सला आपण सबमिट करू. सो इट हॅज रिअली अ मेजर इम्पॅक्ट ऑन and nanorods simply by tuning the hydrothermal temperature time. 80 डिग्रीला 2 तास जर ठेवलं तर नॅनोरॉड्स आले. सिमिलरली तेच 80 डिग्रीला 6 तास ठेवलं नॅनोफ्लेक्स आले. आणि त्या दोघांमधला आम्ही डिफरन्सिएशन बघितलं. कीटोन फॅमिलीला, ऍसिटोनला चांगली सेन्सिटिव्हिटी मिळाली.
केलं होतं सर, ते शेअर झालं होतं.
ऑफकोर्स आपण सगळे फिजिक्स पीएन जंक्शन तर पाहिजे, सेमीकंडक्टर पाहिजे. वी हॅव डेव्हलप्ड जेडेनो अँड CO डोप गॅस सेन्सर बाय युझिंग दी मायक्रोवेव्ह. हायड्रोथर्मलला 2 तास ठेवा, 6 तास ठेवा. त्यापेक्षा म्हटलं आपण मायक्रोवेव्ह ओव्हन मध्ये फास्टर 2 सेकंदामध्ये, 10 सेकंदामध्ये असं व्हॅरिएशन 2 मिनिटाला ते आम्हाला व्हॅरिएशन करून मिळालं.
मी करतो
बेस्ट रिझल्ट आले. दिस वर्क इज पब्लिश्ड इन सिम्पली काय केलं, ते जे सोल्युशन होतं ते मायक्रोवेव्ह मध्ये ठेवलं, पार्टिकल मिळाले, त्याचं डिपॉझिशन घेतलं. ह्या रिएक्शनने ते पीएन जंक्शन झालेलं फॉर्म झाला आणि बेस्ट गॅस सेन्सिटिव्हिटी मिळाली पुन्हा इथे. आणि यू कॅन सी हिअर, मला मी शुअर नाही तुम्हाला दिसत असेल का इथून, फक्त 25 ppm H2S ला गॅस सेन्सिटिव्हिटी मिळाली. बाकीचे सगळे 100 ppm च्या रेंज मध्ये आहेत. आणि तुम्ही बघू शकता की गॅस सेन्सिटिव्हिटी किती छान मिळाली H2S ला. सिमिलरली हे लास्ट आहे गॅस सेन्सिंग मधला SNO2. आपण WO3 बघितलं, जेडेनो बघितलं. भरपूर मेटल ऑक्साइड्स आहेत. 3 ऑक्साइड आहे. 3 ऑक्साइड मध्ये डिफरंट डोपिंग करून आपण गॅस सेन्सिंग बघितलं फॉर्मॅल्डिहाइड साठी. खूप छान इपॉक्साइडने आपल्याला एरोजेल्स मिळतात, जेल्स मिळतात. ते एरोजेल्स न करता आम्ही त्याचं ड्राय पावडर केलं आणि थिक फिल्म बनवून गॅस सेन्सिंग बघितलं. ही काम सुद्धा आपण सगळ्या पेपरमध्ये पब्लिश केलेलं आहे. वन कॅन गो थ्रू दॅट. इट इज व्हेरी इंटरेस्टिंग. So finally, I wrap up this talk. We have seen that the soil gel concepts, a brief manner, soil gel chemistry, alkoxide chemistry, पुन्हा न्यू epoxide route पाहिलं, एरोजेल्स बघितले, फ्लेक्झिबल हायड्रोफोबिक एरोजेल्स बघितलो, वॉटर ग्लास बेस्ड एरोजेल्स बघितलो आपण, ल्युमिनिसंट एरोजेल्स बघितलो. कोटिंग्स मध्ये 5 कोटिंगचे प्रकार बघितलो, सरफेस पॅटर्निंग, TCO, इलेक्ट्रोफोटोक्रोमिक, हायड्रोफोबिक, हायड्रोफिलिक आणि लोके. आणि फायनली गॅस सेन्सर्स मध्ये WO3, जेडेनो, CO, जेडेनो आणि SNO2. With this, I take a pause here. Thank you. Thanks a lot. Any questions? We are open. Questions नाहीत म्हटल्यावर कळलं नाही. Okay. Yes, sir. W3 as a? For battery, sir, these are more Faradic materials. So one can go for battery materials. For example, the better suggestion is nickel cobalt, the nickel oxide based one. These are more suitable for battery materials. These are the best for electrochromic, photochromic. They are good for gas sensors. Since the low band gap, I can say. एरोजन म्हणजे असं इमॅजिन करा, स्पंज आहे, आपण जो पाण्याचा स्पंज यूज करतो, that is the aerogel entirely, but you can have the different fascinating properties. Okay, done. Thank you. Thanks a lot. Thank you, sir.
Next talk by
चांगलं झालं. हं?
आणि ते 3 जे इव्हेंट होते मस्त झालं बाय फॉरगेट मस्त झालं.
हां
शेवटची जी आयडिया होती जुळून
हां
हटके लोक झाला कारण मी झेडो टू बी कॅप्चर केलेलं आहे.
होय, तुला फोन केला होता ना मी.
माहिती नव्हतं.
काय करणार, कुठं प्रोजेक्ट आणणार, कमाल खरा काम करणार.
तुमचं लय कामं केलं.
रिफ्लेक्शन केलं तुम्ही.
मला असं मी 4-5
ना ना लय पिळून घ्यायचा आराम.
पिळून नव्हतं
असं इनोव्हेटिव्ह काम करूच द्यायचं नाही, डोक्यात मुंग्याच टाकतो.
म्हणजे नाही तुझं कसं आहे की तो अनशिवर आहे म्हणजे घाबरतो. म्हणजे समजा
सगळं मुल्ला सरांकडनं.
हा मुलगा त्याला मोशन
होय
मोस्टली
पेपर मध्ये आहे तो मोसिन सगळ्याचा. लय शहाणा तो.
तो अतिशहाणा म्हणजे तो काय करायचा मुलगा म्हणजे सॉफ्ट आहे
हा
बोलायला वगैरे म्हणजे त्याला
हा
मोस्टली भाव तो खाणार
हा
त्याच्या नावाखाली.
होय,
मुलगा सराच्या नावाखाली आला
हे उगीच सिमेंटला म्हणून आपल्याला वाटणार लय भारी माणूस आहे. पॉइंटर जाधव सर. हा
चालतंय का माहिती चालतंय
completed a major research project under the contract in egg science. Yes, you can see. Membership of international solar energy site are yes, international reference center project. I can say American. Its publications are international certified, designated quality, IATF certified, scientific year award, more than 50 books published are over one research projects at the main investigator, one major and one minor, two investigators, one major and one minor. Book chapter and the guide, awarded 1 and 44. They are about the divide of the sample party and awards where each is top 2% scientists of the world. In applied materials and physics, which requires sample as regular and research award, as Swami Ramanathan, Marathon University, also state level, also the star Portrait of Mars, taking the open merit scholarship and possible merit scholarship. Complete biography in the so, as moral presentation, awarded best award in that.
Good morning, everyone. The second international conference on recent advances in material science and nanotechnology, organized by GS Tonpe Mahavidyalaya Sarvajanik Trust, GS Tonpe Arts, Commerce and Science College, Santur Bazar, Amravati, sponsored by Department of Science and Technology, Science and Engineering Research Board, New Delhi. At the outset, I would like to thank the organizing committee of this Raman 2022, that is a international conference on recent advances in material science and nanotechnology. The chairman for this conference, respected principal of college, Dr. R.S. Ramteke sir, another chairman for this conference and director internal quality assurance cell of Amravati University, Dr. Wagole sir, the convener for this conference, respected Dr. Vijay sir, organizing secretary Dr. Devle madam, co-convener and my friend Dr. Ashish Rajgure sir, Pawar madam, and all the organizing committee members of this international conference on materials, recent advances in material science and nanotechnology. I will start my presentation from energy. This is the plan of my presentation. I will be talking about what are supercapacitors, what are Ragone plots, how we can compare between batteries, capacitors, and supercapacitors. And these are the some materials which sir has already discussed about the metal oxides. These are the few metal oxides which we have synthesized at our laboratory in Latur and used them for supercapacitor applications. So, as I told you, I will start my presentation with energy. Now, see, just imagine without energy what we will be. For example, there is no energy for a moment here. My presentation will be stopped. I am speaking on my mic. You are listening through loudspeakers. It will be stopped. So everything will be stopped. So without energy, we cannot imagine the world and the quality of life. It is always decided that how much energy consumption a particular country or per capita energy consumption of a particular country is that. So energy is a very important aspect in human life. And how we get the energy? For example, we say that there is a shortage of energy. When we read newspapers, when we listen to news channels, it is said that there is a shortage of coal. Means we mostly depend upon the fossil fuels for energy applications. Coal is there, oil, natural gases. These are the fossil fuels to which we mostly depend for the energy. And these fossil fuels, oil, or these natural gases, we have a limited reservoirs for these energy sources. And when we have a limited reservoirs for energy sources, and it is expected that the current reservoirs will continue up to 40, 50 years at the current rate of consumption of energy. That means what will be the source of energy after 40, 50 years? Then scientists try to search for alternative energy sources. And we call it as a renewable energy sources or non-conventional energy sources. When you go to the renewable energy sources or non-conventional energy sources, we have wind energy, we have hydroelectric energy, we have solar energy, plenty of sun radiation is available. But when we go with sun radiation, the sun is available during the daytime only. Wind, it is an intermittent source of energy. So we need to capture this energy, sun during the daytime, and use it during the nighttime or when we need it. Or wind energy, we need to capture when it is available, and then we use to when we need it. So how we can use that energy? That can be done through the storage of energy. And therefore, the scientist George Capri, who is the director for Joint Center for Energy Storage Research, he has said that energy storage has the potential to change the way we live. Next year. Next year. Now, most of the countries, they depend upon the hydroelectric energy. That is the one source of energy which can be used. We have a hydroelectric power plant at Koina, which is situated at Satara district. Now China has built a big dam that is called as a 3 charges dam, which has a energy capacity of 22,500 megawatt. This is approximately the daily energy capacity of our Maharashtra state, including Mumbai and Maharashtra. Our capacity is around, during the peak period, we are around 23 to 24,000 megawatt. That is the energy requirement of our state. So China has developed a 3 Georges dam, which is said as an engineering marvel or imminent disaster. They have built a dam with the help of sun radiation, solar energy. They pump this water into the dam during daytime, and they use the hydroelectric generation when the energy is needed. Like that, so this dam was built during the 12 years of a span by around 40,000 workers. But when you store this much large amount of water at one place, for example, this water is around 42 billion tons of water, and that is above the around 180 meter from the sea level. It has changed the Earth's moment of inertia, and Earth started rotating slowly when you store that much water. And it is found that the length of the day it is decreased by 0.06 microsecond. Now we may say that this is a very small time, microsecond and 0.06 microsecond, but it has a big impact on our Earth's rotation and overall environment and climate of the Earth. Next thing. So this is the one thing. Second thing is the global warming. What we feel humidity here, even though there are coolers, fans are rotating, but we feel humidity. The reason behind is that the global warming. When the sun radiation comes on the surface of Earth, it gets trapped naturally by greenhouse gases. And when the radiation is trapped naturally by the greenhouse gases, up to a certain level, that is beneficial for plants and animals. We observe polyhouses, greenhouses. So there, the radiation is trapped and it is used for growth of the plants. But after a certain level of that trapping of energy, that creates a global warming. And that is another reason for use of fossil fuels, thermal power plants, or even when we use the directly diesel and petrol for combustion in our vehicles, that creates a pollution, and pollution results into the global warming. And according to NASA's Goddard Institute, it has been found that Earth's average temperature has increased by 0.8 degrees centigrade. Now you will say that our temperature at Amravati is a 46 degrees centigrade. If suppose earlier it was a 45 degrees centigrade, now it is a 46 degrees centigrade, that is not much difference. But my dear friends, if such a small change in the temperature, what can happen with 1 or 2 degrees centigrade change in the temperature? Now this is the prediction, this is the news from Amar Ujala, where it has shown the impact of a global warming. This is the gateway of India at Mumbai, and the news reads that मुंबई पर मंडराया खतरा, 4 डिग्री तापमान बढ़ा तो समुद्र में डूब जाएंगे यह 7 शहर, और उसमें एक मुंबई अपना जो है वो भी समुद्र में जा सकता है. तो slight increase in the temperature, maybe 1 degree or 2 degrees centigrade due to global warming, it can cause a severe effect on the cities which are situated at the coastal areas due to the melting of ice caps. And it is shown that if the temperature is increased by 4 degrees centigrade, this will be the situation for gateway of India. If it is by 2 degrees centigrade, this is by Climate Central Organization. So these are some drawbacks of using the fossil fuels and the hazards which are created due to the use of fossil fuels. So there are, as I told you, there are alternatives to use the solar energy, wind energy, but solar and wind are the intermittent sources of energy. Hydroelectric is another alternative to pump, using solar and hydroelectric to pump the water during daytime and use it at the night time or when it is needed, but it also has drawbacks. Another alternative to this is the storage of a charge. Now we all know, for example, we have everybody is having a mobile in their pockets. We use the lithium-ion battery for these mobiles. I am using this mic. Inside this mic, there are pencil cells. That is also a battery. Inside this laser pointer, we have a battery. Means we store somewhere energy and we utilize when we need it. So storage of energy, storage of a charge, that is the one alternative considered by the scientists since long back. Now, charging of objects by friction or to store the charge, this is not the new idea. It started a very long back when scientists during the 6th century, when amber is rubbed with animal fur, it was found that it acquired the small beads of charged particles on the amber. Next again. This is the famous experiment you may have performed, charging objects by friction. You can have a comb and you can lift the pieces of papers. There also we have a storage of a charge on the surface of the comb. Another storage device which was used in the early days, it was a Leyden jar. This was the early capacitor. It is said that it is early capacitor, Leyden jar. Next. Then next came is the flat capacitor by Benjamin Franklin. Next. So in this way, initially the capacitors were used to store the charge. We also see a lot of capacitors in our electronic devices. Maybe a kit of a television, maybe a kit of a radio. We see a lot of capacitors inside that, but those are the ordinary capacitors. Then we see a lot of batteries. For example, we have a clock, we have a batteries, transistor, we use batteries, mic, we use batteries, watch, we have a cells that are also batteries. So we already use this storage of a charges mechanism, but the development in the capacitor, it was started in the year 1745 with invention of a Leyden jar that I showed you as a first capacitor. Then there was invention about the electrostatic batteries, then flat plate capacitors, and during 90s, means during the 20th century, there was a research for use of some barium titanate like materials as a dielectric capacitors. Then the first commercialized supercapacitor was developed by Nippon Electric in 1978. Then after that, China, they have developed a lot of supercapacitors. Next. And these supercapacitors in 2002, WAG Public Transport Company in Germany, they tested a bus which used a diesel electric drive system with supercapacitors. Means in China, you can see now the buses which are run over the supercapacitors. Next. This is the invention after 1996. Russia, they developed their electric cars powered by supercapacitors. Then Shanghai High-Tech Park has completed world's first supercapacitor bus fast charging station system. Then we have in 2006, we have a Shanghai 11 has become the first commercial supercapacitor bus line in the world. Then we have hybrid electric vehicles, and then recently in 2019, United States has developed a new type of supercapacitor that can be recharged when it is needed. So this is the bus. This is during the Expo 2019, which is a totally run on the supercapacitors. Here, the bus is stopped at the bus stop. Here, overhead, we have a charging station that is connected to the supercapacitors inside this bus. आणि जर आपण याचा एक विचार केला, समजा शांघाय शहर घेतलं किंवा समजा आपण अमरावती शहर घेतलं, एका बाजूपासून दुसऱ्या टोकाचं जर अंतर घेतलं आणि त्यामधल्या जर बस स्टॉपची जर रचना बघितली आपण, तर साधारण 2 किलोमीटर 3 किलोमीटर आपल्याला सिटी बसला बस स्टॉप असतात. तर प्रत्येक बस स्टॉपला त्यांनी चार्जिंग आणि तो स्टॉप सोडला की ते डिस्चार्ज होईल, परत स्टॉपला गेल्यानंतर पॅसेंजर आत येईपर्यंत आणि उतरेपर्यंत परत चार्जिंग, अशा पद्धतीने पहिली बस शांघायच्या 2019 एक्सपो मध्ये त्यांनी ती रन केली. आता लेटेस्ट डेव्हलपमेंट जे आहे त्याच्यामध्ये विदाउट चार्जिंग मध्ये एका टोकाला चार्जिंग केलेली बस दुसऱ्या टोकाला जाईपर्यंत जाऊ शकते, अशा पद्धतीचं इन्व्हेन्शन त्या बसमध्ये केलेलं आहे. त्याला आपण कॅपा बस म्हणतो, कॅपॅसिटर बेस्ड. सो व्हॉट इज अ कॅपॅसिटर? Then before going to supercapacitor, we should know what is a capacitor. You may have seen these devices. These are the basically capacitor. Capacitor means it is a simple device that stores electrical energy in the form of electric field. Capacitor, it is a simple device that stores electrical energy in the form of electrical field. Next guys. And then we have a battery. Capacitor is different, and then we have a battery. Battery is different. These are the batteries normally you have seen. This is a zinc carbon battery, and in zinc carbon battery, what we have, pencil cell आपण म्हणतो. आपण मार्केट मधून पेन्सिल सेल विकत आणतो. त्या पेन्सिल सेलमध्ये एनर्जी कुठेतरी फॅक्टरीमध्ये भरलेली असते, आपण आणतो, वापरतो आणि टाकून देतो, म्हणजे यूज अँड थ्रो करतो त्याला, आपण रिचार्ज करत नाही त्याला. तर अशी जी बॅटरी असते ती बॅटरी आणि कॅपॅसिटर हे कंटिन्युअसली चार्ज डिस्चार्ज करत असतात. आपण ते डिव्हाइसमध्ये ऑलरेडी सर्किट्समध्ये, इलेक्ट्रॉनिक सर्किटमध्ये आपण वापरत असतो. These are the capacitors. This is basically electronic circuit. This stores, as I told you, this stores of energy in the form of electrical energy in the form of electric field. आता कॅपॅसिटन्स आणि व्होल्टेज त्याच्यामध्ये एक सगळ्यात महत्त्वाचं, जेव्हा तुम्ही रिसर्च करायला लागता तेव्हा तुम्हाला कोणत्या मटेरियल वरती करावं किंवा कोणत्या ऍप्लिकेशन्स वरती करावं ते महत्त्वाचं असतं. तर त्याच्यासाठी महत्त्वाचं जे आहे त्याला आपण जर बघितलं तर इथं काही कॅपॅसिटरचे वेगवेगळे प्रकार दिलेले आहेत, 5 प्रकार दिलेले आहेत आपण, आणि त्याचा कॅपॅसिटन्स किती आणि व्होल्टेज किती आहे ते दिलेलं आहे. तर पहिलं सिरॅमिक कॅपॅसिटर जर बघितलं, सिरॅमिक कॅपॅसिटर क्लास 1, इट हॅज अ व्हेरी हाय व्होल्टेज रेटिंग around 1000 volt, but the capacitance stored it is in the range of picofarad. Whereas ceramic capacitor class 2, it can go up to microfarad, but the voltage that can be used means for charging voltage and discharging voltage, operational window that is lower. Then we have a film capacitor. Again, the voltage is decreased even though the capacitor is increased. Then we have an electrolytic capacitor, wherein we have a voltage, but again the capacitance is a very low, that is a millifarad. But this green one, this is a supercapacitor, where voltage is small, but the capacitance it is in the range of kilofarad. Normally we observe microfarad, picofarad, nanofarad, but the capacitance for supercapacitor it is in the range of kilofarad. Next slide. Then what is the major difference between a battery and a capacitor? Now battery it has a heavy energy, म्हणजे आपण बॅटरी जर सेल जर वापरत असतो याच्यामध्ये काही तास आपण वापरू शकतो, लाईफ स्पॅन त्याचा असू शकतो. कॅपॅसिटर इन्स्टंटली चार्ज होतात, इन्स्टंटली डिस्चार्ज होतात, म्हणजे फास्ट चार्जिंग फास्ट डिस्चार्जिंग असतं. सो द एनर्जी डेन्सिटी इन द बॅटरी इट इज अ व्हेरी हाय. ऍज फार एज द कॅपॅसिटर्स आर कन्सिडर्ड, द एनर्जी डेन्सिटी इज लो. बॅटरीज आर हेवी. आपण सेल पासून जर लिथियम आयन बॅटरी जर बघितली किंवा लीड ऍसिड बॅटरी आपल्या 2 व्हीलर मध्ये असते किंवा घरामध्ये इन्व्हर्टरला वापरतो आपण, ती जर बघितली द बॅटरीज आर हेवी, but capacitors they are light in weight. The batteries are expensive, capacitors are cost effective. The charge speed, batteries take a lot of time to charge. आता इलेक्ट्रिक व्हेकल्स आपल्याला यायला लागले, त्याच्यामध्ये बॅटरी वापरलेले आहेत. आपण बघतो इलेक्ट्रिक व्हेकल चार्ज करायचं म्हटलं तर त्याला टाइम लागतो, पण कॅपॅसिटरला इट कॅन बी इन्स्टंटली चार्ज within fractions of seconds and instantly discharge. So the charging speed for batteries it is slow or it is limited. Then lifespan, battery lifespan is limited. Lifespan for supercapacitors is 10,000 charge discharge cycles like that. आपल्याला बॅटरीचं एक उदाहरण जर म्हटलं, आपल्या मोबाईलमध्ये बॅटरी असते साधारण हजार सायकल, म्हणजे की आपण एक 2-3 वर्ष वापरलं तर त्याची बॅटरी डिग्रेड व्हायला चालू होते. पण त्याचं कारण असतं, मोबाईल खराब होण्याचं कारणच आपण बॅटरीमुळेच आपण जास्तीत जास्त मोबाईल खराब होतात. तर 1000 सायकल 1200 सायकल पर्यंत त्याला चार्ज डिस्चार्ज चांगलं मिळू शकतं आपल्याला. म्हणजे तुम्ही जर दररोज एकदा चार्ज करत असाल आणि डिस्चार्ज करत असाल तर मग 3 वर्षापर्यंत तुमचं जाऊ शकतं 1000-1200 दिवस. पण सुपर कॅपॅसिटरच्या बाबतीत किंवा कॅपॅसिटरच्या बाबतीत तुम्ही 10,000 टाइम्स 20,000 टाइम्स चार्ज डिस्चार्ज केलं तेवढे दिवस तरी त्याला काही फरक पडत नाही. दॅट इज अनदर advantage of capacitors as compared to batteries, that is a lifespan. And the materials used for batteries, they are toxic materials which are for example mobiles we use a lithium ion battery that is creates a lot of pollution, environmental pollution, and lead acid battery also they are toxic, but the material which are used for capacitors they are less toxic. Next. Then apart from this, then we were discussing about batteries and capacitors. What is a supercapacitor? As I shown in that diagram, supercapacitor is a device which has a very high capacitance. मग हाय कॅपॅसिटन्स कसा येतो आपल्याला माहिती आहे. आपण जेव्हा कॅपॅसिटन्स डिफाइन करतो, आपण 2 पॅरलल प्लेटचा कॅपॅसिटन्स डिफाइन करतो, वी से दॅट द कॅपॅसिटन्स इज डायरेक्टली प्रोपोर्शनल टू द एरिया ऑफ द प्लेट अँड इट इज इनव्हर्सली प्रोपोर्शनल टू द डिस्टन्स सेपरेटिंग देम. म्हणजे कॅपॅसिटन्स इट इज डायरेक्टली प्रोपोर्शनल टू एरिया अँड इनव्हर्सली प्रोपोर्शनल टू डिस्टन्स. आणि मग आपण जेव्हा लिहितो C इज इक्वल टू ε0 A divided by a constant टाकून आपण A divided by D लिहितो. Supercapacitor uses this principle. That is, the effective area of the plates which is used in the supercapacitors is a very high. So A is a very high, and the separation is a drastically reduced. Means D is a reduced. So numerator is increased, the denominator is reduced. So the total ratio it is increased, and in this way the capacitance it is in the thousands of farads. So that is the main difference between an supercapacitor and ordinary capacitor. Then another important thing about the ordinary capacitor which we use in electronic devices in supercapacitor is a charge storage mechanism. Now when we have a ordinary capacitor, we have a two parallel plates and a dielectric medium is inserted between the two parallel plates. When you apply the electric field, dipole formation takes place and electric energy is stored in the form of dipoles in this dielectric material. But whereas the supercapacitor stores more energy than ordinary capacitors by creating a double layer, as the separation is a very small, it creates a double layer between the two plates and charges are accumulated on these plates. In this way, with a bigger surface area and small separation, supercapacitor can store more amount of charge as compared to ordinary capacitor. Apart from this, supercapacitors have excellent electrochemical performance. It has a high specific power, superior cycling life, rapid charging discharging rate. These are the names. When you search on Google or internet, you will find these many, or books: ultra capacitor, electrochemical capacitor, gold capacitor, electric double layer capacitor, pseudo capacitor, power coaches. These all are the names of supercapacitors. Next हे झालं कव्हर केलं. So where the supercapacitors can be used? There are various applications of supercapacitors. Regenerative braking to release the power in acceleration. Normally आपण काय करतो, समजा अमरावतीमध्ये आपण कार ड्रायव्हिंग करतो. आपण काय करतो, अमरावतीमध्ये समजा आपण 30 किलोमीटरच्या एनर्जी 30 किलोमीटर पर आवरच्या स्पीडनं चालले आणि पुढे अचानक स्पीड ब्रेकर आला किंवा व्हेकल आला, आपण ब्रेक करतो. ब्रेक केल्यानंतर 30 किलोमीटर पर आवरचं स्पीड आपण एका काही फ्रॅक्शन ऑफ सेकंड मध्ये, लेस दॅन अ सेकंड मध्ये ते 0 किंवा 5 किलोमीटर पर आवर मध्ये आणतो. आणि मग तेवढी जी कायनेटिक एनर्जी होती त्याची, बघा आता कारचं वजन समजा एक क्विंटल धरा, 1 टन धरा, समजा 1000 किलो धरा, त्याची स्पीड धरा 30 किलोमीटर पर आवर, त्याची तेवढ्या मोठ्या प्रमाणामध्ये असलेली कायनेटिक एनर्जी आपण काय करतो, ब्रेक प्रेस करतो. ब्रेक प्रेस केल्यानंतर काय होतं, ते टायरचं आणि रोडचं फ्रिक्शन होतं आणि जी काही कायनेटिक एनर्जी होती ती सगळी हीट एनर्जी मध्ये वेस्ट होऊन जाते. दोन गोष्टी होतात, एकतर एनर्जी वेस्ट होते आणि टायरचा विअर अँड टिअर म्हणजे घासतं, त्याच्यामुळे टायर पण खराब होऊन जातं. तर सुपर कॅपॅसिटर आता जे रिजनरेटिव्ह ब्रेकिंग जे आणलेलं आहे त्याच्यामध्ये काय केलं जातं, आता ही जी कायनेटिक एनर्जी आहे ती इन्स्टंटली आपण बॅटरीमध्ये चार्ज करू शकत नाही. मग त्याला एक पर्याय काय आहे, तर सुपर कॅपॅसिटर. तिथं रिजनरेटिव्ह ब्रेकिंग मध्ये सुपर कॅपॅसिटर वापरले जातात आणि तुम्ही जेव्हा इन्स्टंटली ब्रेक करता, ब्रेक केल्यानंतर जी एनर्जी कायनेटिक एनर्जी तुमची जाणार होती, ही 1 टन समजा त्याचं वजन असेल 1000 किलोग्रॅम आणि 30 किलोमीटर पर आवर, त्याचे जे काही साधारण 33,000 जूल एवढी एनर्जी होते साधारण, रफली आपण अप्रॉक्सिमेट काढली तर 33,000 जूल एवढी एनर्जी तुम्ही इन्स्टंटली सुपर कॅपॅसिटर मध्ये स्टोअर करू शकता. आणि ती आयडिया आता रिजनरेटिव्ह ब्रेकिंग मध्ये वापरली जाते. त्याच्यामध्ये मग टायर वरती लोड न येता, फ्रिक्शन न होता, ते एक पहिलं ऍप्लिकेशन जे आहे सुपर कॅपॅसिटरचा रिजनरेटिव्ह ब्रेकिंग, दॅट इज नॉर्मली युज्ड इन इलेक्ट्रिकल व्हेकल्स. आता जे इलेक्ट्रिकल व्हेकल्स वापरतो आपण, टू रिलीज द पॉवर इन ऍक्सेलरेशन. नेक्स्ट आहे लोडिंग अँड अनलोडिंग ऍक्टिव्हिटीज. जेव्हा तुम्ही एखादी वस्तू, समजा जिथं बंदर आहेत किंवा जिथं लोडिंग, जिथे इंडस्ट्रीज आहेत मोठ्या प्रमाणामध्ये, तिथं लोड आणि अनलोड करावं लागतं. जेव्हा आपण लोड करतो तेव्हा त्याला मोमेंटरी पॉवर जास्त लागते त्या क्षणाला. त्या क्षणाला पॉवर जास्त देण्यासाठी पॉवर डेन्सिटी जास्त असते सुपर कॅपॅसिटर मध्ये, म्हणून लोडिंग आणि अनलोडिंग ऍक्टिव्हिटीज. देन टू स्टार्ट पॉवर इन स्टार्ट स्टॉप सिस्टम्स इन इलेक्ट्रिक व्हेकल्स, टू डिलिव्हर हाय पॉवर अँड ब्रिज पॉवर गॅप्स. Then supercapacitors can be used for industrial and electronic applications. They are used in wind turbines, electric and hybrid vehicles. विंड टर्बाईन एवढ्यासाठी, तुम्ही जर कधी विंड मिल बघितले असेल तर त्याचं जे विंड टर्बाईन असतात ते खूप मोठे असतात, म्हणजे मोठ्या आकाराचे असतात. छोट्याशा वाऱ्याला ते सुरू होऊ शकत नाही समजा, पण त्याला जर फिरवायचं, स्टार्ट द्यायचं असेल, इनिशियल मोमेंटम द्यायचं असेल आणि वारा जर छोटा असेल तर त्या ठिकाणी तुम्ही सुपर कॅपॅसिटरचा वापर करून त्या ठिकाणी आपण सुपर कॅपॅसिटर कॅन बी युज्ड इन विंड टर्बाईन्स, इलेक्ट्रिक अँड हायब्रिड व्हेकल्स. टू रेग्युलेट व्होल्टेज इन एनर्जी ग्रिड, जर फ्लक्च्युएशन व्होल्टेज मध्ये होत असेल तर त्या ठिकाणी आपण वापरू शकतो. To capture and assist the power in lower loads and lifted loads, backups the power in quick discharging state. याच्याशिवाय स्पेसमध्ये नासाचे जे काही स्पेस शटल आहे त्याच्यामध्ये सुपर कॅपॅसिटर्स हे ड्रिल मशीन त्या ठिकाणी जे स्पेस शटल मध्ये वापरले जातात तिथं आपण वापरू शकतो. नेक्स्ट, त्याच्यानंतर जे या बॅटरीज आहेत ज्या स्पेस शटल मध्ये वापरले त्या ठिकाणी सुपर कॅपॅसिटरचे ऍप्लिकेशन्स आहेत. नेक्स्ट, आता रॅगोन प्लॉट ज्याला आपण म्हणू की ज्या प्लॉटवरून सगळ्यात कोणतं मटेरियल, सरांनी मगाशी सांगितलं की लॉट ऑफ मेटल ऑक्साइड्स he has used for gas sensing applications or other applications. ते जे कोणतं मटेरियल आहे ते तुमचं सुपर कॅपॅसिटरला येऊ शकतं का, तर ते डिसाईड करण्यासाठी आपण हा जेव्हा कॅरेक्टरिस्टिक स्टडी करतो वी प्लॉट दिस ग्राफ आणि मग वी नीड अ डिव्हाइस विच हॅज हाय पॉवर डेन्सिटी ॲज वेल ॲज हाय एनर्जी डेन्सिटी. आता पॉवर आणि एनर्जी मध्ये काय फरक असतो? एनर्जी डेन्सिटी म्हणजे किती वेळ एनर्जी देऊ शकतो आणि पॉवर म्हणजे काय की एक इन्स्टंट पॉवर किती देऊ शकतो, एका क्षणाला तुम्हाला किती देऊ शकतो, हे महत्वाचं असतं. मग याच्यामध्ये जसं समजा फॉर एक्झाम्पल आपल्याला 1 क्विंटलचं पोतं उचलायचं आहे. पॉवर जर असेल तर 1 क्विंटलचं पोतं उचलू शकतो आपण आणि एका जागेवरून दुसऱ्या ठिकाणी नेऊ शकतो. पण जर पॉवर नसेल तुम्हाला तर मग तुम्हाला एनर्जी वापरावं लागते. मग तुम्ही 1 किलो घ्याल, 2 किलो घ्याल, नेऊन ठेवाल, असे परत जात राहाल. म्हणजे एनर्जी डेन्सिटी आहे तुमच्याकडे, तेवढी एनर्जी तुमच्याकडे आहे पण पॉवर नव्हती, मग तुम्हाला ते पोतं उचलता आलं नाही. तसं वी नीड अ high power density as well as high energy density, and hybrid supercapacitors, they provide a way to this device which provides high power density as well as